The equation of conservation of energy, also called energy principle, is based upon the first law of thermodynamics, namely, the rate of change of energy of the mass system equals the net rate of heat flux into the system minus the rate of that work is done by the system. This can be expressed in equation, and this is a scalar equation. The energy of the mass of the fluid consists of potential energy of the mass, kinetic energy of the fluid mass, and internal thermal energy. For a control volume of fluid, the energy can be expressed as shown here with the sum of the potential energy, kinetic energy, and internal energy. Students, in this equation, the vertical elevation Z is measured above a datum and always positive upwards. G is the gravity acceleration, and rho is the fluid density, for example, 998.2 kg per cubic meter for water at standard condition. Note that the pressure P is not shown because it is part of the work term. The work comprises the pressure work and the non-pressure work terms. Usually, the pressure work is added to the energy of the mass of the system, and the equation of conservation of energy is often rewritten as shown here, with the introduction of the non-pressure work term. Students, the non-pressure work includes the work of the shear stress done on the adjacent external fluid in motion, and the work done on rotating elements, for example on hydraulic machinery. The internal energy per unit mass is associated with the temperature of the fluid, considered incompressible here in first approximation. When the change in temperature of the flow is small, the variation in internal energy is small, and the equation of conservation of energy can be expressed as shown here. Let us now consider a steady open channel flow, assuming a hydrostatic pressure distribution. When the streamlines are parallel to each other and to the invert, the pressure gradient is hydrostatic, with here the distance y being measured normal to its invert using the sketch as a reference. For a constant open channel discharge, and after transformation and simplification, the equation of conservation of energy can reduce as the variation with distance of this quantity d cos theta plus z naught plus v squared over 2g equal minus the slope of the total energy line. The term in bracket on the left-hand side is called the total head, and the units are meters. Students, the total head, big H, is proportional to the total energy, with this expression here assuming hydrostatic pressure distribution. In the expression of the total head, the first term is proportional to the pressure work, the second term to the potential energy, and the third term to the kinetic energy. Now coming back to the energy losses in open channel flow and pipelines, the head losses or energy losses are a combination of regular losses, for example by friction, and singular losses, which are localized, such as in hydraulic jump, shown here. Students, the concept of regular and singular losses are commonly applied to pipe flow and open channel flow. Regular losses are uniformly distributed along the channel on the pipes, and the head loss along a distance big L is typically expressed as shown here, delta H head loss equal F times L over dH times V squared over 2G, where dH is the equivalent pipe diameter. Singular losses are localized and typically expressed as delta H equal K times V squared over 2G, with K being the singular energy loss coefficient. The equation of conservation of energy is a fundamental principle in fluid mechanics, including its application and use in physical modeling and numerical modeling of fluid flow. This is discussed in a number of relevant YouTube video movies in the same channel.